Right. We're looking at practice problem 6, which I've just pulled up. The geneticist P.M. Shepard carried out a selection experiment on a laboratory population of the fruit fly Drosophila melanogaster. The stubble allele, which affects bristle shape of the fly, is dominant to the wild type allele. Flies that are homozygous for stubble always die during embryonic development. Okay. So he starts out with 86% normal flies and 14% stubble flies. So calculate the allele frequencies. And let's do this on the whiteboard. Right there. Let's enlarge that a bit. Okay, so we start out with, okay, stubble is dominant to wild type. But flies that are homozygous for stubble die during development. This is called an embryonic lethal, and it's not that uncommon. So we can flies with a genotype that we can write as big S, embryonic lethals. Those flies are never born. Big S, little s flies have stubble, and little s homozygous flies have normal straight bristles. Okay, so we start with a population with 86% normal flies, which have genotype SS, and 14% heterozygous flies. Okay, first of all, calculate the allele frequency. The simple way to do this is just to remember that if you have a population where you just have percents, but you don't have raw numbers, the frequency of any allele is equal to the frequency of the homozygotes plus half the frequency of the heterozygotes. So the frequency of the little s allele is 0.86 plus 0.07, which is going to be 0.93. If you want to do it the long way, this works out the same. It's not really necessary to do it the long way, but I don't really care how you work these problems. So the long way is pretend that we have a population of exactly 100 flies. So we have 86 flies that have genotype little s, and 14 flies that are heterozygotes. So if we have a population like that, then the frequency of big S is equal to the number of, the number of homozygotes times 2. Number of homozygotes is 0 because big S flies are never born, times 2, plus 14 flies that have 1, divided by the total number of alleles, which is 200. So you can basically, it's 14 over 200, which is 0.07. And then the frequency of the little s allele is you have 86 flies out of 100 that have 2 of each allele. You have 14 flies out of 100 that have 1 of each allele. You divide things by the total number of flies of alleles in the population, which is 200. If you have 100 flies, you have 200 alleles. And 86 times 2 is 172. Add 14, 172 plus 14 is 186. And that's 186 divided by 200 equals 0.93. So you can do it the long way if that will keep you from getting yourself mixed up. You can reduce this by algebra and show that the frequency of big S right here is just the frequency of homozygotes plus half the frequency of the heterozygotes. So it's 0% plus 0% plus 7%, which is 7% or 0.07. And the frequency of the little s allele is 0.86 plus half of 0.14. So it's 0.86 plus 0.07, which is 0.93. But if you don't care to remember that, you can just drop the percent signs and pretend you're working with a population of 100 flies. So we'll call that number Q, and our 0.07 we'll call P. All right, so there's our allele frequencies. Assume for right now that wild type and stubble flies don't differ in fitness. Use the allele frequencies to calculate mean fitness. Okay, the first thing that we've got to do is calculate a number that's called mean fitness. And to do that, we have to calculate fitness values for all of these genotypes. Here's how we do it. For the flies of each genotype, we find some number that carries information as to how many get to reproduce. And then we take all three numbers that we've got and divide them by the highest of the numbers. So how would we do that? We represent fitnesses by lowercase letter w's. So we have to calculate something called W big S, W big S little s, and W little s. And these, again, these would normally be written with subscripts, but I can't really do that on this whiteboard. Okay, how do we calculate what those are? All we're given is the knowledge that stubble bristle flies and normal bristle flies don't differ in fitness, which means that in any population, some stubble-winged flies die before they get to reproduce. They get eaten by spiders or infected with myxozoan parasites or whatever the heck it is. And only some fraction of stubble flies gets to live. And I'm going to call that X. That's the fraction of stubble flies that survive and reproduce. We don't have to know what X is. What we know is that the fraction of normal flies that gets to survive and reproduce is the same, because the problem tells you that stubble and normal flies don't differ in fitness. So X could be 0.1, it could be 0.5, it could be 0.9, it doesn't really matter. It's the fraction of flies that survive to reproduce successfully. And whatever it is, it's the same for the stubble flies and the normal flies. And for the big S flies, we can calculate it, it's 0. Because if you are a fertilized fly egg that has big S genotype, you are never going to become a living fly at all. For whatever reason, you end up so messed up that you're never born. Okay, so what? So we have these three numbers, 0, X, and X, that express the probability of survival for flies of each genotype. Now we take the largest and divide all three by that largest number. So of 0, X, and X, which is largest? Well, it's X. Unless X is equal to 0, which means that no flies ever survive at all, and we don't have a problem to begin with. If any flies survive, that means X has to be greater than 0, because some flies have to have a non-zero probability of reproducing, or else the population just vanishes. So X is the biggest. So we divide each term by X, like so. And 0 divided by X is equal to 0. X divided by X is 1. And X divided by X is 1. So the mean fitness of, or the, not mean fitness, we're not there yet. The fitness of the flies with the big S genotype is 0. And we can set the fitness of flies with the other two genotypes to 1. This is a relative probability. It doesn't mean that all of the flies are guaranteed to reproduce. What it just means is that flies in these two phenotype classes have equally good probabilities of reproducing. Neither one is better than the other. Okay, now what? Now, we need a new equation. There, put that there. And this is going to take a bit of room. All right, you may have noticed, am I going to have enough space to write it? I better. Okay. You may have noticed that P plus Q must equal 1, right? Okay, P plus Q is equal to 1. That means that P plus Q squared must equal 1, right? Because 1 squared is equal to 1. And that means that P squared plus 2PQ plus Q squared equals 1. And the three terms of this equation are the frequencies of the three genotypes in a 2-allele Hardy-Weinberg problem. Okay, that should be fairly easy. What we're going to do is we need to add something to this. So to calculate something called the mean fitness, I'm going to take P squared and multiply it times the fitness of the associated genotype. P squared is what the frequency of big S flies would be if there were no selection. P squared times W big S is the frequency of big S flies since there is selection going on. And then 2PQ times W big S little s. 2PQ is the frequency of big S little s flies if there is no selection happening. Multiplying it by that W big S is how you model the effects of selection that is happening. And then Q squared times W little s. Q squared is what the frequency of little s flies would be if there was no selection. And that W little s is the way you model the effect of selection when it is taking place. And if you calculate all of this, you don't get 1, you get a quantity. Am I in black? Good. You get a quantity called W bar. And I always have to come in and draw the bar. Remember, a bar over a number is a way of showing that it's a mean, an average. And so W bar is the mean fitness. And you may have noticed that it's not going to be equal to 1. In fact, what is it? Well, to calculate W bar, oops, lost the bar. That's one thing biologists should never do, is lose a bar. Okay, so to calculate it, P is 0.07 times 0.07 times 0.07 times 0. And that's easy because that whole term is going to be equal to 0. And then the next term is 2 times 0.07 times 0.93 times 1. And then the next term is 0.93 times 0.93 times 1. And that is going to be equal to our W bar. So I am going to whip out my calculator and plug and chug this. And that's 2 times 0.07 times 0.93. And that's equal to, well, the first term is 0, 0.07 times 0.07 times 0. And the second term is 0.13. And the second term is, or the third term rather, is, come on, Wagner, 0.93 times 0.93, 0.865. All right. And so if I add these, of course, I get 0.995. And that, again, is our quantity called W bar. There. There's our bar, being fitness. Okay. Now what? Now what I've got to do is take this equation up here and go back and divide every one of these terms by W bar. So, all right, I'm going to draw lines underneath. This is easier when I'm working with chalk, of course. And so I'm going to divide that term by W bar. And then I'm going to divide this term by W bar. And then I'm going to divide this term by W bar. And then I'm going to divide this term by W bar. Okay, sorry that took a minute and this looks a little bit messy, but I'm taking each one of these terms in the equation that we drew and dividing the entire equation through by W bar. So of course, W bar divided by W bar, you know, this thing right here, that's going to be equal to 1, right? Anything over itself is equal to 1. But let's look at these other terms in here. See, here we have P squared times the fitness of the big S genotype divided by W bar. We can kind of regroup this a little bit. And we can say this is P squared multiplied by this fraction. Now, P squared by itself, that would be the frequency of big S flies if we did not have any selection going on. W big S divided by W bar tells you the effective selection right there. As if W big S is less than W bar, then this part of the fraction, W big S divided by W bar, that's going to be less than 1, right? If the numerator is smaller than the denominator, the fraction is going to be less than 1. And in fact, in this case, that fraction is going to be 0. So 0 divided by W bar is going to be something less than 1. In fact, it's 0, but 0 is less than 1, I think. So what that tells you is that that is our frequency of big S flies with no selection. You're multiplying it by a fraction that evaluates as less than 1. And that tells you the frequency of big S flies after 1 generation will be less than what it would have been if there was no selection. Or here, 2PQ, that would be the frequency of heterozygotes if there were no selection going on. Then we would be in Hardy-Weinberg equilibrium. We'd be meeting the criteria for being in Hardy-Weinberg. No selection, it would just be 2PQ. That fraction right there, W big S divided by W bar, that represents the effects of selection. Well, W big S is 1. W bar is a little less than 1. It's 0.995. So our denominator, come on, Wagner. Our numerator is larger than our denominator. It's 1 divided by something a little less than 1. That means this fraction, W big S over W bar, that fraction is going to be greater than 1. And if you multiply 2PQ by something that's greater than 1, you get something larger. Yes? So that's telling you that after 1 generation, the frequency of heterozygotes is going to be larger than it would have been if there wasn't any selection taking place. And the same thing goes here. Q squared is what the frequency of normal bristled little s flies would be if there were no selection. These terms model the effects of selection. And W little s divided by W bar is 1 over 0.995, and that's something greater than 1. So that tells you the frequency of normal bristled flies is going to be greater than it would have been if there was no selection happening. So that's the way I like to think about it. So let's go ahead and evaluate this thing that I have just done. We take this equation that I wrote down here. What the heck, I'll highlight it. Okay, we take that and we divide the entire thing by W bar so that on this side of the equal sign, we just get 1 again. And so what we get is 0.07 times 0.07. Learn to type, Wagner. Plus 0.07 times 1, times, come on, Wagner. 0.07 times 0.07 times 0 divided by 0.995. That's going to be the frequency of big S flies after 1 generation. And then our next term is 2 times 0.07 times 0.93 times 1 divided by 0.995. Just a sec. Let me see if stretch that box out if I can. There we go. That term is going to be our frequency of heterozygous flies after 1 generation. And then this term is going to be 0.93 times 0.93 times 1 divided by 0.995. And that term is going to be our frequency of little s flies after one generation. And that's equal to 0.995 divided by 0.995, which is equal to 1. So now we have a modification of the Hardy-Weinberg equation. And what we've done now is we can model the effects of selection. So right here, it's not eraser, I don't want that. Okay, I do want this. All right, right there, and right there, and right there is the parts of the equation that model the effects of selection on genotype frequencies. If all of the relative fitnesses were the same, then all of these things that I've just highlighted would be 1, and we'd be back in Hardy-Weinberg land where there wouldn't be any selection happening. But the fact that these are different is how you model selection having differential effects on different genotypes. Okay, so this term right here, all of, I keep trying to work out, there, that, no, I want a different color. This, that's our frequency of big S flies in the next generation. And our frequency of big S flies after one round of selection is going to equal 0, because there's a 0 right there. Okay, so in the next generation, we will not have any big S flies, because that's an embryonic lethal and they're all going to be dead. Okay. This term right here, I don't want that color. There, let's do this in green. That is going to be the frequency of heterozygous flies in the next generation. And that is going to be, he said, flipping out and grabbing his computer, 2 times 0.07 times 0.93 times 1 divided by 0.995. And that is 0.131. So our frequency of, you guys can't read that. Hang on. There. That should be slightly more legible. All right. Okay. So our frequency of I don't know why I'm getting the rainbow effect here. Our frequency of heterozygous flies is going to be equal to 0.131. Sorry if this is getting a little messy. I'm still wrangling the whiteboard controls. So our frequency of heterozygous flies is going to be 0.131. Our frequency of big S flies after one round of selection is going to be still 0. And our frequency of normal bristled flies is that. And so our frequency, not that colored dummy. And so our frequency of of normally bristled flies, little s, is going to be 0.93, not 0.093. That's an error. Times 0.93 times 1 divided by 0.995. Oh, 0.93 times 0.93 times 1 divided by 0.995 equals 0.869. Ugh. Okay, there's our answer. After one generation of fruit flies, after one round of selection, our frequency of big S flies is still going to be 0. Our frequency of stubble bristled flies is going to be 0.131, or 13.1%. So it's going to go down, but it will go down less than it would have if those big S flies were capable of surviving. And our frequency of flies with normal bristles is going to be 0.869, or about 87% instead of 86%. So the frequency of normal bristled flies will go up a little. The frequency of stubble bristled flies will go down a little. The frequency of big S flies will remain 0. Okay, you with me there? I'm going to hope so. I have not seen any pleas for mercy coming through on the chat. So I'm assuming everybody is either getting this or you've all just passed out into a confused slumber. These things do occur. All right. I'm going to erase some of this and we'll go to the next stage. Let me erase a lot of this, in fact. At least we don't have to clean the erasers after. Okay, we're going to have to rethink fitness now, because the third part of the course of the question states that Shepard added an extra wrinkle. He removed 60% of the wild type flies before they were capable of breeding in each generation. So now we have to repeat part B, taking this into account. Okay, so what we now have to do is figure out the fitness of each of the 3 genotypes. And see what those are. Okay, let's again come up with some number called X that represents the probability of a fly successfully reproducing. Okay, well, the probability of a fly with big S reproducing is, again, absolutely 0, right? These flies are going nowhere. Okay, the probability of a big S little s fly surviving is X, and the probability of a little s fly surviving and reproducing is X. That represents the probability of not dying from ordinary causes. That's the probability of a fly reproducing without getting eaten by a spider or getting parasitized by myxozoan fungal parasites, or whatever can, getting sprayed by an angry housekeeper with Raid, all of the things that can kill a fly. The probability of that not happening to you is X. But we have to add something else, because not only do little s flies have a certain probability of dying before they get to breed, they also have a probability that the experimenter is going to take them out. And Shepherd is removing 60% of the wild type flies before they can breed. So we have to calculate their fitness as, dang it, there, X times 0.4. So X is the probability that a fly survives whatever other sources of mortality there are. But the fly also has to survive the probability that Dr. Shepherd is going to vacuum him out and feed him to his toad or whatever you do. And that probability is only 0.4. Shepherd is not doing this to his stubble bristled flies, so we don't have to multiply that in. Okay, see what I'm getting at? Because he's not selecting out the stubble bristled flies, he's not removing any of them from there, then the only things that would cause them to not reproduce are the things that every fly is subject to. All right, so now we do what we did as we did before, and we divide all of these by the largest value. And the largest of those three is X. X is greater than X times 0.4, and X is also greater than 0. So if we divide all three of these terms by X, what we get is 0.4, 1, and 0 again for our fitnesses. This doesn't mean that big S flies are guaranteed to reproduce. It just means that relative to all of the other flies in the experiment, they have the highest probability of reproducing. Right. Technically we'd get the right answer if we didn't do this, but it also makes the math a little bit easier if we take whatever the highest fitness value is and we just set it to 1. Okay, so those are our fitnesses. Now we're going to write the big ugly equation. P squared times the fitness of the associated genotype plus 2pq times the fitness of the associated genotype plus q squared times the fitness of the associated genotype is equal to W bar. Let me dang it. Sorry, it's hard for me to grab a proper hold with the cursor on this silly thing. There. Okay. Now I have figured out how to do it. Okay. So P squared times W big S plus 2PQ times W big S little s plus Q squared W little s is equal to W bar. So there's our bar. So our next step is to calculate that. So that turns out to be 0.07 times 0.07 times 0 plus 2 times 0.07 times 0.93 times 1 plus 0.9, myself more, dang it. Where'd my whiteboard go? Okay, all right, I hope everybody can see that. Times 0.93 times 0.93 times 0.4, all of that is going to be equal to W bar. All right, so we can plug and chug. 0.07 times 0.07 times 0 is, of course, equal to 0. So that's 0 plus 2 times 0.07 times 0.93 times 1 is 0.13. And then the next term is 0.93 times 0.93 times 0.4. And that's 0.346. And that is equal to 0.476. That's our mean fitness for the population. So now what we're going to do is, I'm going to jot that down over here. W bar is equal to 0.476. Right there. All right. So we calculated that. Now what? Now we want to divide all of, did I just do that? Okay, looks like I just did. Sorry, I deleted all of that a little bit early, but W bar is equal to 0.476. We have calculated that. There we go. Now what we're going to do is divide all of this through I'm going to divide that and that and that and that by our W bar. And hang on, let's add the bars. So we're dividing every term in our equation by W bar. All right, what's that going to do? Think it through. I apologize if this is not the most fascinating thing that we have ever done, but it is important that you know what it is that you're doing. So remember, P squared is the frequency of big S individuals if we didn't have any selection going on. 2pq would be the frequency of heterozygotes with no selection, and q squared would be the frequency of homozygous little s flies if there wasn't any selection. If there wasn't any selection, all three of these fitness values would be equal to the mean fitness, and all of these fractions, all of these fractional parts, there, and there, would just equal 1, and we'd be back with the simple Hardy-Weinberg equation. But W big S divided by W bar, that's going to be 0 divided by 0.476, right? Which is 0. So in the next generation, we will have no big S flies because that's an embryonic lethal. W big S little s right there is equal to 1, and 1 is going to be divided by 0.476. Well, 1 divided by something less than 1 must be something greater than 1. So our frequency of heterozygotes is going to be larger than it would be if there wasn't any selection. Right? If there was no selection, our frequency of heterozygotes is just 2pq. If there is selection, then our frequency of heterozygotes is 2pq times something that's quite a bit bigger than 1. Okay, and multiplying something by a number that's bigger than 1, your answer is bigger than what you started with. And for 2q squared right here, q squared would be the frequency of normal bristled flies with no selection, but we're taking that and multiplying it by, this is going to be 0.4 divided by 0.476. Numerator's less than the denominator, so this right here is going to be less than 1, and that multiplying a number by something less than 1, your answer is smaller than what you started with, right? So our frequency of normal bristled flies is going to be smaller than it would be if we had no selection, and our frequency of stubble bristled flies is going to be larger than it would have been if we had no selection. All right. And that's what these fractions that I've circled here are telling you. They're telling you the direction that selection is going to move those genotypes. Okay, and remember that this right here, that's going to be equal to the frequency of big S flies after 1 generation of selection. That's going to be your frequency of heterozygous flies after 1 generation. This is going to be your frequency of homozygous recessive flies after 1 generation. Okay, so how do we calculate that? Well, this is going to be intensely annoying, but this is going to be 0.07 times 0.07. Stretch that out to make sure we've got enough room. Yeah. Yeah, see, the problem is once okay, there, times 0 divided by 0.476. And then the second term is going to be 2 times 0.07 times 0.93 times 1 divided by 0.476. And then our next term is going to be 0.93 times 0.93 times 0.4 divided by 0.476. And that's all going to add up to 1, because lest we forget, right, W bar divided by W bar is always going to be equal to 1, no matter what W bar happens to be. Okay, so evaluating that, we get, well, first of all, our frequency of big S flies is still going to be 0. No change there. Our frequency of heterozygous flies is going to be clear. It's going to be 2 times 0.07 times 0.93 times 1 divided by 0.476. And that comes out to 0.27. It's actually 0.274. And then this third term is going to be there, 0.93 times 0.93 times 0.4 divided by 0.476. And that is 0.727 is what I got. Okay, and the sum of all of those should add up to 1. It does close enough. There's a little bit of round off error in here, so this adds up to 1.001, but that's just error induced by rounding off. So what we now know is that in the next generation, our frequency of big S flies is still 0, because they never catch a break. Our frequency of heterozygous stubble-bristled flies is going to go from 14% to 27.4%. It's going to double, or almost double. And our frequency of normal bristled flies is going to go down from 86% to 72.7%. So it's going to take a noticeable fall. And that's how you plug fitness in to make predictions for the effects of selection. And I tell you what, I see we have, okay, Temple, you've got a question.
Yeah.
Okay, go ahead.
So I know I'm following along pretty well. It's just that I missed a step or something, but we essentially are doing the same thing that we did with I guess the first part of the question, I guess
Yes.
part A or part B, I don't know. But
Okay. Yeah,
beforehand you said,
the only difference between part B and part C
mhm,
in this question is this. The
yeah,
new
right.
wrinkle is that PC Shepherd is now vacuuming out 60% of his normal bristled flies and probably killing them horribly.
Mhm.
And that's the only difference between part B and part C.
Right. Okay. So when we found the mean of fitness for part B, wasn't
Mhm.
it? It was 0.865, but
No,
I think it
it was
wasn't. Okay.
0.995.
Okay, that's what I'm missing. Okay, thank you.
Okay. All right. I really need a break right now and probably a stiff drink, although I can't have that till the afternoon. I'm going to go ahead and stop recording right now.